Right, okay, appetite regulating proteins. We're not going to look at all of the appetite regulating proteins because there is a gigantic number of them. We're going to mainly focus on leptin and ghrelin, which more later. These images are examples of misleading vintage ads about the dietary benefits of sugar from the US during the 1950s and 60s. A common phrase used in the ads was the Appestat, with the advert including the definition from a dictionary stating that it is a neural centre in the hypothalamus believed to regulate appetite. As we'll see, the hypothalamus is involved in appetite regulation, but not in the way that these adverts imply. This was decades before the discovery of appetite regulation hormones, of course, and the concept was purely used to promote sugar consumption. And there's another one. Our understanding of the physiological regulation of appetite has moved on considerably, and we now know that this is much more complex than these simplistic or misleading adverts. It still pops up in unscientific concepts. There was a bakery coffee shop in London called Appestat, but that was closed evidently permanently. It went out of business during COVID. Homeostasis, which is a concept which you did in first year in Appetite and Society, but we'll revisit it here to provide a foundation for the rest of things we're going to talk about. Well, that's old Hippocrates. He noted the human body's remarkable ability to return to an equilibrium state, and that most people recover from illnesses without the intervention of a physician. However, it may be worth mentioning that the lifespan of average ancient Greek was 37 to 41 years. Moving on, Claude Bernard in the 19th century noted the remarkable ability of the human body to maintain its internal temperature, despite the working environment being freezing cold or sweltering hot. Later on, Walter Cannon, working in the early part of the last century, coined the term homeostasis to describe this tendency to maintain internal stability. Homeostasis has been described as one of the most enlightening theories in physiology. It is seen as a group of mechanisms for maintaining physiological equilibrium, with the loss of homeostatic control leading to illness and possibly death. However, it has limitations, and these physiological controls only work effectively within a relatively narrow set of ranges, which we'll talk about a little bit in a while. Normal body temperature varies diurnally, that is over 24 hours, ranging between 37.5 between 10 in the morning and 1800 in the evening to about 36 centigrade between 2 in the morning and 6 in the morning. Again, a diurnal cycle is one that reoccurs every day. Outside this relatively narrow range, significant problems can arise. At temperatures above 42, proteins, including enzymes, may be damaged and may be partially denatured, for example. Below 36 degrees, the rate of enzyme-mediated reactions falls, impacting on cellular and bodily functions. Although outside of the scope of this lecture, if you want to know more about the regulation of body temperature, click on the second image or see the URL and notes. As usual, images often have links, and the notes will have the links if not in there. We never stop. A car only needs energy when it's moving. Humans are different. We need energy at all times of the day, and all throughout our lives. However, living systems, although being on all the time, there are factors such as our metabolic rate, which changes in the day due to circadian rhythms, again a 24-hour cycle, and activity level. So the activity level on the top right is for a hypothetical person who, after waking up, did an hour of exercise on an exercise bike, walked a mile to work and returned home after lunch. What happened to that is unknown. You remember the concept of basal metabolic rate, the amount of energy expended while at rest in a neutral temperature environment in a post-absorptive state, meaning your digestive system is inactive, which requires about 12 hours of fasting, which many of us will get if we don't eat after about 7 in the evening and eat again at 7 in the morning. That's 12 hours, obviously. There's a calculator there if you want to remind yourself about working out your BMI. As always, Armando Hazragun is well worth watching. The link in the image and slide notes is for if you're watching outside of the lecture. So I mentioned the hypothalamus. The hypothalamus is located below the thalamus. A part of the brain that relays sensory information, and above the pituitary gland and brainstem. It's about the size of an almond, and it is very involved in the control of homeostatic systems. Again, circadian rhythms refer to 24-hour bodily cycles. Yeah, so in 1775, the physician Charles Blagden demonstrated homeostasis by spending 75 minutes in a presumably large oven set at 127 with a dog and a beefsteak. He sweated, the dog panted, and the beefsteak, which being dead was unable to maintain homeostasis, was cooked somewhat, probably not to the point where it would be safe to eat. His report to the Royal Society was the first demonstrating the role of sweating in thermoregulation. He was also, it's often claimed, the first person to define the concept of a chemical reaction, one of the foundations of modern chemistry, which you all have enjoyed throughout the course of the degree. Feedback mechanisms. Positive feedback involves a response that reinforces the change. It's said to function to amplify the change. So if you cut yourself and don't do this at home, platelets produce platelet clotting factor, and the more they produce, the faster the factor is produced, so rapidly clotting the wound. Negative feedback is more important for homeostasis. It occurs when physiological conditions change from the normal state and acts to return that body to this state. So there's a continuous cycle of events in negative feedback for all of our homeostatic systems, and there are very many of them, as briefly mentioned earlier on. So here's a classic example, broken down into both what happens in a generic flow chart. If the body temperature rises, this is detected by sensors in the skin, leading to activation of temperature regulation systems, such as sweating, for example. And as I mentioned, the second flow chart is a generic view of the process and applies to all such feedback mechanisms, not just biological ones. So here's some definitions. Again, there's that flow chart again. The set point is the physiological value at which the body normally fluctuates. So the set point for human body temperature is 37 degrees centigrade. The change detection is receptors in the body, such as in the skin, which detect changes in the relevant parameter and relay information at the control centers of the brain, such as the hypothalamus. And the effector is that something that brings the body back into equilibrium, sweat glands, etc., in the case of temperature. Okay, we'll look at a nutrition-related example, the regulation of blood glucose. Remember that if you see a term in square brackets like this, it should be read as concentration of, in this case, blood glucose. Before we start, a quick reminder of cellular respiration, and then we'll look at the storage and release of glucose. He did this in human metabolism, and I believe you've revised it a little bit recently. It's a highly concerted redox process where the carbon atoms in food molecule, principally sugars, but also amino acids, lipids, and ethanol, are oxidized to carbon dioxide, while respiratory oxygen is reduced to water. This takes place during glycolysis and the citric acid cycle, and the energies from this process and the electron transport chain is used to regenerate ATP from ADP, and that's literally why we eat and why we breathe. Although not shown here, the electron transport chain reoxidizes reduced forms of coenzymes like NAD and FAD. See the video link there, it's got the yellow background, for a nice walk through electron transport chain if you want to remind, and also the resources in this link to glucose and citric acid cycle. I'm not going to go through the many rows of ATP here, you should be familiar with that material, but I recommend having a look at those two or three videos. Okay, glycogen. Glucose circulates in the bloodstream to provide energy for cellular reactions via the cellular respiration mediated regeneration of ATP we talked about in the last slide. It's stored in the form of the polysaccharide glycogen. It's mostly stored in the liver, and the liver of an adult male weighing 1.5 kilograms can be about 10 to 15% of weight by glycogen, which is why animal liver, is said to taste starchy. I don't know whether that's true of human livers, and I don't really want to know. It's also found in smaller amounts, 1 to 2% by weight in the muscles and in skeletal muscles of an adult weighing. So the skeletal muscle of an adult weighing 70 kilograms stores about 400 grams of glycogen, obviously ready for immediate use. Insulin is a peptide, a relatively short protein with 51 amino acid residues. It's classified as a hormone. That is a molecule produced in one part of the body, the pancreas, which carries a signal to another part of the body, the hypothalamus in this case, producing a physiological change associated with controlling the concentration of blood glucose. So in a sense, insulin was the first appetite-influencing protein to be discovered. Glucogen is the flip side. Smaller protein with 29 amino acids, residues, again, is a protein hormone involved in controlling blood glucose. We'll talk about what they do in the next slide. What slide is coming up anyway. Brief mention of the endocrine system, again going back to first year. You might want to dig your notes out. Blood glucose concentration regulation is one example of a much wider endocrine system. This is a messenger system consisting of feedback loops, positive feedback loops generally, negative feedback loops generally, of the hormones released by internal glands of an organism directly into the circulatory system, regulating distant target organs. In vertebrates, the hypothalamus, as discussed, is often the control centre. And in human, the major endocrine glands are the thyroid glands and the adrenal glands, which is why when appetite regulating proteins produced by the gut were discovered, it's quite a surprise. Yeah, okay, so there's a little diagram of feedback mechanisms involved in control of blood glucose concentration. The levels of which are detected by alpha and beta cells in the pancreas. The image actually links to a good resource in the anatomy of the pancreas, but you don't need it specifically as a module as far as I know. Normal blood glucose levels before meals, that is often technically described as pre-prandial, between 4 and 5.9 millimoles per litre, and after 90 minutes a meal, said to be postprandial, under 7.8 millimoles per litre. If you want to click on the want to know more about blood sugar level ranges, click on the link for details from UK Diabetes. Yeah, so this otherwise nice image has blood glucose levels as a percentage I was talking about in millimoles previously. It's a bit annoying, but don't worry. There are calculators available, but we don't really need to worry about that, just the relative differences. If blood glucose rises above the normal range, pancreatic beta cells produce the hormone insulin. This promotes the synthesis of glycogen, so reducing the amount of glucose in circulation, and the spelling of that in the notes is totally wrong, so I'm sure you'll figure out. Just advance the slide a bit. Yeah, so as a summary, when a person who does not have diabetes has high blood sugar, insulin is produced by the pancreas, and this promotes the storage of glucose as glycogen. Conversely, if such a person has relatively low blood glucose, the hormone glucogen is produced, promoting the release of glucose in the bloodstream by the hydrolysis of glycogen into glucose. Okay, I'm going to stop the video here. We're 12 minutes, so I'll be back with part 2 fairly soon.